Okay, this is the supplementary lecture, lecture number 3. So in previous lectures, lecture 1 and 2, and also the previous lecture 3, we pretty much introduced the basic information about polymers, such as their definitions, their kinds, and their structures, such as configuration and conformation. And at the end of the lecture number 2, we have seen that molecular weight or the size of polymers matter because they are quite related to the properties such as mechanical, chemical properties. Okay, and if you make polymers, polymers are really polymers are basically the species with long chains, and the length of those chains are not uniform, which means that there are variations or the distribution of the length of polymers. Some of them are longer, some of them are shorter, okay? Which means that the molecular weight of polymers, unlike that of small molecule, have a distribution or the average value. And there are 4 different kinds of average molecular weight of polymers. We already have seen these 4 different kinds, right? Number average, weight average, Z average, and viscosity average molecular weight of polymers. You guys already have seen the definition of them, and I also uploaded the additional website link which uh, uh, differentiate these two, number average and weight average molecular weight. And the other two, the Z average or viscosity average molecular weight, are not that important compared to these two, number average and weight average ones. The reason why is that the number average and weight average molecular weights are related to the other polymeric properties. For example, number average molecular weight is related to the physical property of polymers such as glass transition temperature. I believe that you guys all have done the basic experiment in sophomore, right? And uh, there you guys have done the DSC measurement for polymers, right? And uh, for the measurement of DSC, you guys measure the glass transition temperature of polymers, right? And that value is related to the molecular weight of polymers, especially the number average molecular weight. So we'll get back to this point later when you learn about the glass transition temperature in more detail. Similarly, weight average molecular weight of polymers are related to the flow or rheological behavior, such as like what is it? When you learn in fluid mechanics, right? There's some behavior of rheological properties, and some of those polymers are related to this. And this part is not quite discussed in this class, but anyhow, when you learn about polymer physics in more detail, you learn about this more. Okay? So anyhow, there are 4 different kinds of average polymer molecular weight, and in general, they have this trend. The number average is smallest, followed by viscosity average, weight average, and Z average. And as I mentioned, since there are distribution of polymer chains, the length of polymer chains are not uniform. It is almost impossible to make monodisperse polymers, which means that the all average molecular weights are same. The reason why is that because we are basically living on Earth. If you synthesize polymers in space without any gravity, then it could make monodisperse polymers. And also, when we learn about the polymer synthesis, there's a way to pretty much synthesize the close to monodisperse polymers later. Okay? All right. So let's see an example. So this part is not covered in previous video lecture. Let's consider a case at which we blend two different polymers. Okay? There's sample number 1, there's sample number 2. And this sample number 1 has number average molecular weight of Mn1 and weight average molecular weight of Mw1. Similarly, sample number 2 has number average molecular weight of Mn2, weight average molecular weight of Mw2. Okay. And we want to calculate the number average molecular weight and weight average molecular weight of this blend. Okay. Then, since we know that the number average molecular weight is basically defined as the weight divided by the number of moles, right? The overall weight of the total samples divided by total number of moles, right? Okay, and total number of if you want to calculate the total number of moles, you can use these relations here. So, for example, N1 is basically the sigma I and I, which means that in this sample, for example, there will be distribution of the different length of polymer chains, right? So, for example, N1 is the number of moles of polymer chain number 1, like the length is, for example, 1, and 2 is different chain length, and 3 is different chain lengths, etc. Okay? So, N1, basically the total number of moles would be weight divided by the number average molecular weight. Because number average molecular weight is weight divided by number of moles, right? So you can use these relations to calculate this. So by putting this N1 and also N2 using these relations, you can put this and this, okay? And for example, if you have information about the weight of each sample, for example, you added this sample number 1, for example, like A kilogram, and sample 2 is like B kilogram, then we have information about this weight. Okay, and we also have information about the number average and weight average molecular weight. So if you have information about the weight of each sample of the blend, then you could easily calculate the number average molecular weight of the blend. So for example, if you divide numerator and denominator by W1 plus W2, then you could have these relations. Basically the same expression. Okay? See here, W1, small W1 and small W2 means basically the weight fraction. Okay? Similarly, weight average molecular weight could be obtained a little bit more easily, right? Weight average molecular weight, the definition is shown here, right? This is the definition. Okay, we could easily get these relations by the weight definition of the weight average molecular weight of each sample, right? Weight average molecular weight is basically given by this here, right? Remember this definition here, okay? Here. So if you put it here, you could easily get the relations, basically definition of the weight average molecular weight of the blend shown here. Okay. So if you have information basically about weight average molecular weight and also the weight, okay. So we have the weight information about the weight, how much sample 1 and sample 2 are mixed together, then we can easily calculate number average and also weight average molecular weight. Okay, so you can find some examples of like this kind of calculation in the textbook as an example and also as an exercise. Okay, so you can do the simple calculation. Okay, so we have just seen that there are 4 different kinds of average molecular weight for polymers, right? And how could we determine, how could we measure it? There are many different ways, So we guys already have seen some of them. Okay? I'll just briefly review. There are two different kinds, basically two different methods, absolute method and relative method. So absolute means that by using this kind of method, we could determine the absolute value of molecular weight. Okay, and relative method is like we can determine the relative molecular weight, like the comparison. Okay, and among absolute method to determine molecular weight of polymer chains, there are many different ways actually here, right? And using many different like experimental method, we could determine like number average, weight average, or even Z average molecular weight. And to determine number average molecular weight, a few different experimental methods can be used. One of them includes end group analysis, such as titration and NMR, or colligative property. You guys already have learned about this in general chemistry and also physical chemistry class, right? But for example, like BP elevation, but it's not really easy to use for polymer samples because yeah, like instead of like colligative property, that's why we use osmotic pressure to determine molecular weight of polymers. Because when you heat up the polymer samples, it could degrade the polymer samples, so it's not really easy to determine the number of the molecular weight using like BP elevation. There's a way called light scattering. I believe that you guys also do this experiment in your third year, right? So you might do it this semester, some of you, right? So I briefly talk about this light scattering later here at the bottom of here, this slide. And centrifuge is used to determine Z average molecular weight. And relative method include viscometry and GPC. By doing viscometry, we can determine viscosity average molecular weight, and by doing gel permeation chromatography, you can determine the molecular weight distribution of polymer samples. So let's briefly see a little bit more details about some of the experimental technique. The first one is called light scattering. And by doing light scattering, we have seen that we can determine weight average molecular weight. So it's here. The basic principle is very simple. Okay, so let's read it. Large particles in solution, suspension, basically, suspension scatter light. It means that if you have, for example, some, kind of like polymer, it's not easy to draw a picture, PDF file. So there's some, for example, like solution, and there's a polymer particles, something like this. This is polymer particles with a certain size, okay? And if you shine light, right, with some kind of light source, for example, like laser, okay, some of the light hit these polymer particles and scatter it, okay? Basically, these small sized particles scatter light depending on like the wavelength of the light, etc. And the degree of scattering basically depends upon the size of the polymers, and size means basically the molecular weight. Okay, and that molecular weight is weight average molecular weight in this case. Okay, so as shown here, extent of scattering is a function of size and shape of the particles. And in usual cases, we just assume that these shape of polymer particles are basically the spherical. Okay, and we kind of tend to make the environment of this polymer solution at which polymer samples form relatively spherical shape. Okay, there's a way. We'll probably see it about this when you learn about polymer solution. Okay? Soon in lecture 4 maybe. Okay? It's a very simple principle, and I believe that you guys do this experiment in third year, probably soon, hopefully. So very simple, right? We just briefly introduce the way. And second method is called viscometry, and viscometry is already covered in previous video lecture. Right? We simply use the polymer solution and with a very small capillary, and by simply checking the time between these measuring lines, we could determine the viscosity of the polymer solution, and that viscosity is related to the viscosity average molecular weight, MV. Okay? And this by doing this viscometry, what you determine eventually is this value, right? This value here, this value is called actually this is the limit of the reduced specific viscosity as concentration approaches 0, and that value corresponding to this A0 is the single polymer contribution to viscosity. How one polymer attribute like to the overall viscosity of polymer solution, and that information is basically depends on the viscosity average molecular weight. Okay. So let's assume that we determine this, okay, this value, and this value is related to, as I just mentioned, viscosity average molecular weight MV following this equation, which is called Mark-Hoink equation. So this eta bracket eta is equal to some constant k times viscosity average molecular weight to the power of a. Okay, and this k and a are constant, which can be obtained by basically doing experiment, by doing this kind of viscometry measurement. Okay, here k and a are empirical parameters, characteristics of polymer and specific solvent. Okay? So these values basically depends on the polymer environment, what kind of polymer you are measuring and what kind of solvent they are in. Okay, so for example, for well-coiled polymer in a poor solvent, so we haven't learned about this polymer solution yet. It'll be covered in lecture number probably 4, right? Right? Lecture number 4. So poor solvent basically means that the solvent does not really dissolve the polymer samples. Okay, in those cases, polymer would be kind of form well-coiled structures, right? Because polymer and solvent don't like each other, right? So it's not really dissolved in solvent. Okay? In those cases, this A value usually have approximately 0.5. Okay? On the other hand, for rigid rod-like polymers, means that here we said that polymers are well coiled, like a spherical shape, and quite oppositely, this is like rod-like polymers. Polymer chains are like expanded. Okay? For example, expanded coil in a very good solvent. Right? If solvent like polymers very much, then they could mix together and they dissolve it, right? Though in those cases, A corresponds to 0.8. There's also a relation between this eta and Rg, and Rg is called radius of gyration. Okay, and radius of gyration is something like this. there's many different ways to determine the size of the polymers, and one of the way is called the radius of gyration, and we'll learn about this later soon in lecture 5 or 6. Let's say that polymers form well-coiled spherical shape. So there's polymer chains like this. Okay, so overall polymer looks like sphere. Okay, the radius of this sphere of the polymer samples, right? Radius of this sphere is called radius of gyration. Okay, got it? Okay. So this eta value correspond to these, basically follows these relations with radius of gyration. So there is some constant phi and Rg to 3 Rg cubic over molecular weight m. Okay. So from here, you guys already have seen that this eta is equal to some constant k times mv to a, right? So when a is 0.5, when a is 0.5, okay, so if you put 0.5 here, right here, okay, so this eta is basically proportional to m.5, right? M to the 0.5, and there is another m. Okay, if you multiply m to both sides, then the left side will be proportional to m to the 1.5, right? Then the Rg, radius of gyration, will be proportional to m to the 0.5, right? Similarly, if a is 0.8, then Rg to 3 would be proportional to m to the 1.8, right? Then Rg would be proportional to m to the 0.6. Right? So depending on the environment of the polymers in a specific solvent, the radius of gyration have different relations with the molecular weight. Okay? All right. And another technique which could determine the relative molecular weight is called gel permeation chromatography, or GPC. Okay, we already have covered this part in a previous video lecture. By comparing with the standard samples with non-molecular weight, okay, we can determine the unknown sample with unknown molecular weight. So for example, let's see an example. So let's see, we got GPC data, something like this. Okay, so the x-axis is time, and y-axis is intensity. Okay, and we by the principle of the GPC, okay, we know that when the time is short, the elution time is early, it has a higher molecular weight, and it is late, then it's smaller molecular weight. And let's see that at this peak, there's two peaks for this GPC chromatogram. The first one is molecular weight of 100,000. The second one is 10,000, with the intensity of relative intensity is 2 and 1. Okay, and we know that this intensity, the signal peak size, is proportional to the mass of the polymer samples, right? So if you have this kind of GPC chromatogram, you can easily determine the number average and weight average molecular weight of these samples. Okay, how? You already have seen these relations, remember? Right? From this example, you have already seen this example, right? So similarly, you can use similar relations. Basically, the definition of weight, number average, and weight average molecular weight. Okay. So since we have the intensity or the signal size, which is proportional to the weight, is mass, okay, which means that we have information about this weight. Okay. So weight is basically 2 to 1. Okay, and we have information about the molecular weight, 100,000 and 10,000. Okay, so by simply having the GPC data, okay, basically molecular weight and also the intensity, you can easily determine number average and weight average molecular weight as shown in these examples. Okay? You can do it by yourself. Okay? Then there could be a question. What if we have calibration curve for polystyrene, but the unknown sample is PMMA, quite different ones, right? PS and PMMA are quite different polymers. Okay. What could you do, right? Can you determine the molecular weight of PMMA if you have calibration curve something like this for PS? It is possible. The reason why is that GPC basically separates chains based on volume pervaded by coil. Okay? Which means that different volume, basically volume means mass, right? Different volume of samples have different molecular weight, basically different elution time, right? Different elution time here and here. Okay, so which means that from these relations that we have just seen, right, the relation between the what's it called, the eta and the radius of gyration. So since the radius of gyration is defined as the radius of spherical shape of the polymer samples, right, polymer chains, Rg to the 3, Rg cubic, third, this one, basically proportional to the volume of the polymers, right? Okay, which means that this eta times molecular weight is basically proportional to the volume. Okay? Then, even for different samples, different kinds of polymers, this eta times molecular weight would be same. Okay, if the elution time is correspond to each other. Okay, so for different samples, PS, PMMA, this eta times molecular weight would be same with each other. Okay, then you can use Markov equation, this equation. Okay, but here Markov equation is only applied to viscosity average molecular weight here. Okay, this one. So this one is different. This molecular weight is different from this one. Okay, this is just the this molecular weight is different from the viscosity molecular weight, viscosity average molecular weight. So in this case, we need to assume that the sample is monodispersed. Okay? If the sample is monodispersed, MV, MW, MN are all same. So we can just use Km to the A. Okay, then you put this eta here, Kma to here and here. Okay, then you get these relations. Okay, so if you have information about K values for polystyrene, K values for PMMA, and also molecular weight of PS, and also some constant A here, then you can determine the molecular weight of other sample PMMA, okay, using these relations. Okay. You could find an example in the textbook using these relations to determine the molecular weight of the unknown sample based on calibration curve of other polymer samples. The way is osmotic pressure, right? So we all learned from physical chemistry class that the osmotic pressure is a kind of colligative property, which is only dependent on the amount or the moles of the samples in solution, right? So remember the Van Hoff equation, pi is equal to CRT, right? Remember? So similarly, you can use this relation using polymer samples. So based on these kind of relations, it's not that important. Just you can just read it a little bit by changing the like solvent, ghost solvent. We haven't really learned about theta solvent anyhow. You can use different kinds of solvent with a kind of polymers. Okay, by changing the concentration, you can basically get this kind of experimental data, okay? And by taking this concentration to the zero concentration, you can easily determine the molecular weight here, okay? the number average molecular weight by taking this limit. So it's simple, just physical chemistry class. Okay, so this is pretty much it for the lecture number 3. Okay. Okay, this is the supplementary video lecture number 4 on polymer solubility and solutions. So in previous lecture, we have learned about the molecular weight of polymers, and in doing that, we have briefly introduced the polymer solutions in like different solvents, etc., right? Such as like radius of gyration. So if you dissolve polymer samples in a specific solvent, which solvent will dissolve which polymers? Okay. Basically, dissolving means like interaction with each other, between polymers and solvent, right? And we all know these general rules. For example, like the simplest one is like dissolve like. Okay. For example, if the polymers are polar polymers with like polar substituents, and if the solvent is polar solvent, then they will like each other. Okay, polar solvent probably most possibly dissolve polar solvent and polar polymers. Sorry. Okay. So although there are several like general rules for polymer solubility, we need more like details. So you guys already have seen these general rules about polymer solubility in previous video lectures. So let's see some other aspects of polymer solutions. The first one is thermodynamics. Okay, we all know that in thermodynamics, the most important variable is Gibbs energy, Gibbs free energy. Okay, so for example, if polymer dissolved in a certain solvent, then the Gibbs energy change upon those like dissolving process would be negative, right? And we all know that from physical chemistry class, that delta G is equal to delta H minus T delta S. Okay? The most important equation of thermodynamics, right? And we already have also learned about this delta X mix. Okay, if polymers are dissolved in solvent, basically polymer and solvent mix with each other, right? You guys already have seen this equation from physical chemistry class. Okay, when you mix two different, like for example, two different ideal gas, or if you form ideal solution, okay, in liquid phase, you guys have already seen this equation, right? And for polymer solutions, the equation for delta X mix is quite similar. It looks like this. Okay, we simply replaced this x1 and x2, the mole fraction of species 1 and 2, with phi 1 and phi 2, which corresponds to volume fraction of the polymers. Polymer and the solvent. The 1 is solvent and 2 is polymer. Okay, so basically, the pretty much looks similar. Okay. How about delta H, the enthalpy change upon dissolving polymer in a solvent? Delta H mix have these relations. We don't know how, but we really go into the details how we get these expressions. We just simply accept this equation. So delta H mix of polymer solution is chi12, some constant called polymer solvent interaction parameter, times RT times N1 is number of moles of solvent, phi 2 is the volume fraction of polymer. So the other parameters are very simple except this chi12 polymer solvent interaction parameter. So as the name indicates, it probably indicates the how the molecular interactions between polymer and solvent, like how large that is, right? So chi12 here is equal to V seg times delta 1 minus delta 2 square over RT. So here V is actual volume of polymer segment, okay? And delta 1 and delta 2 are called solubility parameter. So delta 1 is the solubility parameter of solvent, delta 2 is solubility parameter of polymer. Okay? So it looks a little bit complicated, but we don't really need to memorize them. Just we need to simply understand what some of these variables mean. Okay? So we already have learned about this delta S mix from the physical chemistry class. Okay? So we know that delta S mix is always positive, right? Because there's minus sign here, and these are basically the fraction, okay? Mole fraction or volume fraction, okay? Which means that this part minus T delta S is negative, right? And if the delta G if delta G is negative, which means that delta H should be either negative or even even if delta H is positive, it should be small as much as possible. Okay, so since delta H mix is equal to chi RT and phi 2, which tend to be positive, right? Which means that if chi, the solvent polymer interaction parameter, is small, then this delta H will be small and overall delta G will be negative. Okay, and this chi12 is small, which means that this is positive, like volume, right? Delta 1 and delta 2, if those two values are similar to each other, right, then this chi12 will be close to 0, right? So overall thing, if you understand the overall principle, then the solubility parameter, we don't know what those are, but if the solubility parameter of solvent and polymers are similar to each other, then they will dissolve with each other, like solvent will dissolve polymers. Okay, that's pretty much it. Okay? That's pretty much it that you need to understand. Then basically, what does this solubility parameter mean, and how can you determine it experimentally and also theoretically? Okay, that's the next slide. So this delta is called solubility parameter or Hildebrand solubility parameter. Hildebrand is the name of the scientist. So this scientist Hildebrand kind of determined this delta value solubility parameter not for all systems. These are only apply for non-polar, non-hydrogen bonding solvent. And these values are given for many different systems. Let's see an example here, right? For different solvent, different polymers, these delta values are already given. Many scientists have already determined them. Okay? And these delta values are used in many different applications, for example, in industry. Okay? And we already have seen that if these delta values are close to each other, they basically like each other. Okay, so when you need to select solvent or prediction of compatibility of polymer, etc., you use this delta value. Okay. Then how can you determine this delta value? Okay. What exactly determines, what kind of molecular properties determine this delta value, solubility parameter? Okay. So let's do that. First, how to measure intermolecular forces. So let's assume that we have some molecules, solvent, polymer, etc., whatever. Okay. Then the easiest way to determine intermolecular forces is to heat it up. Okay. You just heat up, for example, some solid or liquid samples, and as the temperature goes up, at some point it reaches boiling point and it will evaporate. Okay. Then by measuring the delta H upon evaporation, we can determine the intermolecular forces, intermolecular interactions of the samples in liquid phase. Okay, that's the most easiest way. But the problem is polymers do not evaporate. If you heat up the polymer samples, as I mentioned, that they degrade. Okay. So anyhow, we want to determine the intermolecular forces of the polymers or solvent. Okay. So the interactions like intermolecular forces are called cohesive forces if the if the interactions are between the same molecules. If they are between different molecules, it is called adhesive forces. Anyhow, we want to determine cohesive forces now. Okay. So let's denote epsilon 1 as cohesion energy per binary contact. So if there are two molecules, okay, the intermolecular interactions between these two molecules basically is cohesion energy per binary contact, E11. Okay. Okay. Then cohesion energy per molecule for a single molecule would be E11 over 2, because there is, if this is a binary contact, the interaction we just calculate, we double calculate, right? For this one and also for this one. Okay, so we need to divide it by 2, and also we need to multiply by coordination number. Okay, if there is only 2 molecules, it's 2. If there are like 4 molecules, right? I'm sorry. Let's say there's 1 molecule, and if there are, for example, 4 different molecules surrounding this molecule, and for this one, there are 4 different interactions with this one, here, right? So we need to multiply by this one, okay? Z, coordination number. Then there's another variable called cohesive energy densities, or CED. CED is the the definition of CED is cohesion energy per unit volume. So this is the cohesion energy. So if you divide it by volume, okay, that is CED, cohesive energy density. Okay. And if you can determine this CED, the definition of Hildebrand solubility parameter is root CED. That's all. Okay. So which means that this delta has the meaning of cohesive energy, right? Cohesive energy of same molecules. Okay. The detailed like derivation or like equation is not that important. Okay. The meaning is important, right? The definition of delta, Hildebrand solubility parameter, is root CED, okay? Cohesive energy density, okay? Cohesion energy per unit volume. Okay? So which means that this solubility parameter has a meaning of cohesion energy of the same molecules. Okay. So basically quantitative measure of interaction energy between molecules. It's simple, right? So the detailed equation is not important. So people have already determined this Hildebrand solubility parameter for many different solvent and polymers. You can clearly see that for example, like for non-polar solvent is relatively small. Okay? On the other hand, if the solvent is like polar, alcohol, ethanol, like water, is much higher. Right? It's obvious, right? Polar solvent have much higher interactions, molecular interactions. It's similar for polymers, right? Non-polar polymers have relatively small values of delta. Uh, polar polymers, like polar polymers, have a little bit larger, delta values. Okay. So the definition of Hildebrand solubility parameter is very simple, and there should be a way to determine it theoretically and also experimentally. So first one is the experimental method. Okay, so you guys have already seen this from the previous lecture, video lecture, right? Okay, you can either measure intrinsic viscosity for soluble polymers, or you can determine the maximum swelling for lightly cross-linked polymers. Okay? If you have, for example, unknown polymer samples, and if you want to determine the delta values for that polymer samples, you can simply dissolve it in different solvent with different values of solubility parameter. Okay, then you can determine it. So this is a experimental method, and theoretically, you can also do the theoretical calculation doing some group contribution using group contribution theory. I don't know the details about this, but anyhow, since the solubility parameter is based on the cohesive energy density, right? Somehow, if you can determine the cohesive energy density, then you can determine the over the CED and also the resulting delta value. Okay? And if you know the value of delta for solvent and polymers, you can determine the compatibility, right? If polymer and solvent have similar delta value, which means that they tend to dissolve with each other. Okay? Compatibility, solubility. So here, so compatibility also could mean different polymers, right? If two different polymers have similar delta value, which means that they tend to mix with each other, right, without doing phase separation. Okay? Solubility also swelling degree of rubber, right? If the polymer is like lightly cross-linked polymer such as rubber, then if that rubber and the solvent have similar delta value, then they would have like very large swelling. Okay? But the problem is we already have, if you recall the assumption that, let me get back, of the solubility parameter, it is only applied to non-polar, non-hydrogen bonding solvent. It's basically limited to specific cases. So some of the limitations that in some cases, although thermodynamically delta G is negative, but in some cases, in some systems, the solvent does not dissolve polymers. There's exceptions, right? And delta H cannot be negative. And I mentioned that it's only applicable to only this dispersion force for non-polar systems. Okay? So there, another person, which is called Hansen, made new concept of new solubility parameter. Okay? And in this case, this Hansen guy considered different kinds of molecular interactions, not only the non-polar dispersion force. He included hydrogen bonding, dispersion force, and also polar interactions. Okay? So he included two more molecular interactions, and by considering these three interactions, he could determine the Hansen solubility parameter. Okay? But even though he considered these other types of molecular interactions, this Hansen solubility parameter also has limitations. Okay? So, for example, it varies with temperature, and even these three molecular interactions are not enough. Okay? And solubility parameter also depends on molecular size and conformation, and this information, size and conformation, uh, is not included in this molecular interaction. Okay, so this is pretty much it for lecture number 4, right? So we have learned that about the polymer solubility, and how can we determine which polymer, like which solvent. Okay? And basically, you guys need to understand the basic principle, right? Thermodynamically, basically, what determines the feasibility of the polymer solvent dissolving is solubility parameter delta, and delta value the Hildebrand. The Hildebrand solubility parameter is determined based on the cohesive interactions between molecules, and people already have determined them, and we can use those values for some applications, and also we can determine delta value doing some experiment for swelling or viscometry measurement, etc.